our next speaker of the day is my co-chair, Morten Scheibye-Knudsen, and here I would like to take a little bit longer introduction because, we owe this to Morten. I call aging research and biogerontology the mixed martial arts of biotechnology. So you need to be able to master many fields to be able to innovate. And I think that if we compare aging and biogerontology to MMA, Morten is the most complete fighter because he is MD, PhD. So he did his MD at the University of Copenhagen. He did his PhD at the University of Copenhagen, focusing on neurodegeneration and accelerated aging. And then he did his postdoc. And then he was a research fellow and a postdoctoral professor at the NIH and the National Institute on Aging in Baltimore. So NIA is actually located in Baltimore, working with the all-famous Rafa Di Cabo, who is also the editor of Gerontology Section A, as we all know. Very hardcore journal, very great journal as well. And that's where we met. So one of Morten's students and somebody who just recently founded a company, Turn Bio, Michael Petter, he used to be an intern at Insilica when we were still in Baltimore and at the Emerging Technology Centers at Johns Hopkins. Later, Michael moved to Copenhagen and started working doing brilliant work. So very happy to see that progress. But also it's important to highlight that, in the spirit of Robert Langer and George Church, Scheibye-Knudsen's lab also serves as an active platform for biotechnology entrepreneurship and academic industry partnerships. So I am representing a company, we collaborate openly, we publish together, and companies like Turn Bio, Arsalus, and many others were born out of his lab, and many venture capitalists and pharma companies draw their inspiration and strategy from Scheibye-Knudsen's lab. And while this conference connects us all, many of us are also plugged into Scheibye-Knudsen's lab via academic collaborations, industry partnerships, and just general research. So very happy to be introducing Morten, and he is going to be talking about the interventions in premature aging. Thank you.
Thanks, Alex. Just one small, so I have nothing to do with Turn Bio, it's Track Bio, but really appreciate everything you said. I remember meeting you the first time at a tiki bar, I think, which was outside my home in Baltimore, where we had some great discussions. So it's been a long journey, but I'm very happy that we met, Alex. I'm going to talk about interventions in premature aging. So yesterday we saw Vadim define aging with some different definitions. I like this very simple definition that aging is a time-dependent increase in risk of death. And that sort of translates into a risk of death curve where you have your risk of dying the next year as a function of your age. And as we can see, when we get older, at some point, it really starts to increase a lot. And when we hit 121, your risk of dying the next year is about 100% because that's the world record. Men are a slightly higher increased risk of death than women. We all know that. And this risk of death can then be translated into a survival curve. So this is the survival curve of the Danish population. As a function of age, people tend to die. And this is maybe not that interesting. What is more interesting is that we can actually look at prescription data that we have from the really amazing registries we have in Denmark, and look at how prescriptions are associated with differences in lifespan. And we have a poster here, Michael Ben Ezra will talk about that. So each line here is a cohort of individuals that have been given a certain prescription drug. And you can see that some are associated with a lifespan, with a longer lifespan, and some are associated with a shorter lifespan. So one of the first things we looked for was, of course, metformin, which has been heavily investigated by me also a little bit with Rafael De Capo in Baltimore, but also, of course, there's the TAME trial by Nir Barzilai. And if we look at everybody that gets prescribed metformin and how that cohort is associated with mortality, we can see that they actually have a shortened lifespan compared to all. If we look at people that are given metformin when they turn 70, then you can actually see there's a survival benefit compared to everyone. I think the important part here is that there is an underlying reason for why people get metformin, which is diabetes, right? And so even despite having diabetes, the first 10 years, when you're 70 years old, you actually have a lifespan benefit. And this is, I think, interesting also in context of Maria's Amelova's talk yesterday. So there's a confounding by diagnosis, of course, in this data set. We try to avoid that a little bit with looking at drugs that are given to the same diagnosis. So each column here is a separate diagnosis. And then looking at compounds that confer survival benefit to other compounds for the same diagnosis. And there are some that confer survival benefit, some that do not confer survival benefit. We can then look at compounds that are associated with a survival benefit and also associated with a longer lifespan. And these are now compounds we are exploring. And the reason I'm highlighting this is because it also feeds into a very interesting way of funding research and drug development potentially. So I, for a while, or for a long time, worked with some people at Molecule that will be here. I think they'll be here tomorrow, Friday, tomorrow. Can't remember, one of the coming days. They developed a platform of crowdfunding where everybody can put money into drug development, and then they will get ownership of whatever comes out. So the idea is that if you suffer from type 2 diabetes or any other disease, you actually get co-ownership of the drug that you're injecting. And so this is done through this sort of cryptocurrency scheme here. I'm not an expert in this, but the idea is that you can buy tokens, and that crypto token actually holds pieces of the intellectual property. So all of the intellectual property associated with this is actually contained in a token that is owned by this community of people. So I don't own anything of it. I just try to develop it, right? So it's a way to fund research, which I think is interesting. One point is that aging is not magic. Aging can be influenced by drugs. Also, we know, of course, that there are different organisms that age in different ways. Every organism doesn't die at the same time, right? So there's an underlying genetic component of aging. One of the most extreme examples is, of course, the hydra, which doesn't really seem to have any increased risk of death. And if this is our definition of aging, then it doesn't really age. So aging is not magic. Aging is also influenced by our genes, of course. One of the, I think, a strong piece of evidence that is also true is that if you can get single gene mutations, inherit single gene mutations from your parents, and then you get premature aging. This is an area that I've studied quite a bit. Some of the work that I did previously showed that in some diseases where you have accelerated aging, you have issues with repairing DNA, you get an elevated activation of a DNA damage response that then drives loss of certain metabolites. And you can then intervene at certain levels using PARP inhibitors, and that extends the lifespan of prematurely aged worms. This is in mice. We gave them nicotinamide riboside, which is an NAD precursor. And that rescued sort of cerebellar defects in the brain of these mice. We're actually using NR now. We have a trial ongoing together with Elysium, where we're testing NR in COPD. There's a poster down here in the corner to see if we can alleviate sort of lung aging. We can also use ketones, it appears, to increase acetyl-CoA. So DNA repair is important in aging. So what if we could stimulate DNA repair? So the way we do that is, as Suresh highlighted yesterday, what does not kill us makes us stronger, right? We can take advantage of what's called the hormetic response, that if you stress a cell with a little bit of stress, it can cope better with subsequent stresses. And so together with in silico medicine and driven by talented postdoc Gary Magarachichan, we could screen a number of compounds to find drugs that seem to elicit this hormetic response. So we screen about 15,000 drugs in silico. And then we, of course, wanted to investigate if these drugs, we wanted drugs that do not cause DNA damage, but elicits a DNA repair response. We used what's called a COMET assay. Each dot here is a nucleus. And the nucleus is embedded in agar, and there's an electrophoretic field that's run across the nuclei. If there are breaks in the DNA, then the DNA will be dragged out and form these comets here. So the longer the tail, this is called the comet tail or the olive tail moment, the more damage the drug makes. And we want drugs that do not induce the DNA damage. So many of them do not, right? We can see many of them don't really induce DNA damage. But in fact, many of them, or some of them, confer really strong radio protection. So this is cell survival, where each dot here is a separate compound. And you can see some of the compounds make the cells really quite immune to ionizing radiation. So I'm gonna go over time, I see, but I'm also gonna diverge a little bit to a way we then measured whether or not they actually affected senescence or affected aging at the cellular level. So we developed a deep senescent, a senescence predictor that was driven by AI, deep neural networks, and it's really quite accurate. I think you heard Rudy's talk yesterday with an AUC about 0.8. That's really good. This has an AUC of 0.99, so it's really, really good at predicting cellular senescence in vitro. But it actually also detects cellular senescence in other cell types. So it was trained on fibroblasts, so it can detect cellular senescence in increased senescence in prematurely aged fibroblasts. This is from Hodgkin-Gilford progeria patients, Cockayne syndrome, and telangiectasia, but also in senescent astrocytes and even in liver tissue. This is work from Malte in collaboration with Gubra. He's somewhere, I think. And we can actually also see it in the skin of individuals. So with H&E stained skin sections, we can isolate nuclei, and we can use those nuclei as a way to predict senescence. And with age, you get more predicted, particularly replicative senescent cells. And quite interestingly, if you have more replicative senescent cells, we then could go back into the registries and see how does that affect disease. We can see that if you have more senescent cells, you are actually protected from cancer. If you have less senescent cells, you have a higher risk of developing cancer. So this sort of still indicates that senescence is it's good to have the ability for cells to induce senescence because it acts as a stop for proliferation. Obviously, it also says that it doesn't say anything about it's probably still good to remove them once they're there. With senolytics, we don't know that yet. There's a lot of evidence for that. I'm not going to go into that discussion. Anyway, we used the predictor on with our drugs, drug F, our lead compound, and saw that we reduce senescence. And interestingly, since we trained we found the drug through compounds that were supposed to stimulate DNA repair. We looked at what happened with DNA repair foci. And we irradiate the cells, we wait 7 days, it's the standard senescence induction protocol. And then we look at DNA damaged foci, 53BP1 and gamma H2AX. And over this time course, the cells sort of maintain some irreparable DNA damage lesions. And when we treat with drug F, we can reduce these lesions to the pre-damaged state. We also tested then using this TrackBio platform that Michael Peter from the lab developed. We wanted to test the compounds in vivo, and this is like what Matt showed the other day. We have a neural network. We're not detecting worms here, but we're detecting flies. And so we can detect the flies and track them over time. So what we get is, for example, movement data. Each line here is a fly that's been walking around. And when you're a young fly, you walk around quite a bit. When you become an old fly, you walk around a lot less. Unless if you're drug F, you actually walk around quite a lot. And this is sort of quantified here, that you maintain movement. The flies maintain movement on drug F. It also extends the lifespan. So that's good. And quite interestingly, if we look at a hallmark of senescence is, of course, that cells are stalled and they do not proliferate anymore. But giving them drug F, you actually see a restart in proliferation. They start expressing pCNA again, and then you see cell growth that then sort of peaks and then it dies off again. So it's not that they become immortalized. We created a number of analogs also that I'm not going to talk about. So this is, I think, an exciting way to find drugs that may stimulate DNA repair and potentially affect aging. We also have drugs that are trained on UV DNA damage. So this is repaired by something called nucleotide excision repair. And I highly recommend that you visit a poster by Esther Miron, who will stand there, I think, all day and talk about it, where we actually found some compounds that appear to stimulate nucleotide excision repair. With that, I will stop and take any questions. And thank you all for joining this meeting, and thank you for listening to me. While I went over time, I apologize. Thank you.
Most of the questions on Slack. However, there are some questions that were just recently prioritized. And let's say we take a call, the question from Attila Sardas. So were there any drug combos, not just lone riders, that stood out curbing mortality in the Danish data?
This is a great question. We have not looked at it yet, actually, but this is obviously something that we can look at. The database is vast, so there's definitely possibility of looking at something like that. So this is a great idea and something we will definitely look at.
Great. And the question from Morten Scheibye-Knudsen. So Morten, how do you correct for a change in mortality due to treatment of specific disease versus effects on aging?
I mean, this is really a difficult problem, I think. You know, we try to do this by looking at lifespan benefits for drugs that are given to the same diagnosis. So it's true that we don't know how they affect aging, but we do know they are associated with a lifespan extension or associated with longer lifespan. And we also know in all cases actually what the target is of these drugs because they're FDA approved. So we have a good idea about potential mechanisms or lack of mechanisms. So this is sort of what's guiding us, but it's true we don't completely know if this affects underlying aging or specific disease that are associated with aging. I just want to highlight though that the lifespan extensions that are associated with the three compounds that we chose are actually very large, much larger than we see with metformin, for example.
Perfect. And are there any questions on site for Morten? Anyone?
No questions. There is a question from Max.
Yesterday we heard Matt talking about like those 100,000 molecular interventions with the worms. With your platform for Drosophila, what's like your baseline, or what do you think? How much can you do a year?
That's a good question. Where's Michael? I mean, we have a 3D printer, so we can just print out stuff. We have about, how many is running? 200 experiments at a time. So obviously we cannot do it in the same, probably not as high throughput as Matt's, but I think still quite good. Thank you.
Great.
Oh.
So, any other questions?
I think we're good. Thanks, Alex. See you.
Thank you. And big round of applause for